Good afternoon from the UK. Welcome to the 21st Surface Ventures webinar. Before we go any further, I just want to check if everything's working. Can you please write where you are joining us from today in the chat box on the right-hand side. So while we do that, my name is Tahid Khan. I'm a VP at Surface Ventures, and I'm your host for today. We are a non-for-profit organization, and our mission is to provide world-class surface engineering education for academia and industry. So every month, we bring to you a sector-leading speaker to present the current challenges and future trends in surface engineering, alongside surface engineering workshops and live equipment demonstration. Great. It seems like everything's working, and there's many great places there. So today it's my pleasure to introduce Professor Ling Wang, discussing integrated intelligent bearing systems for UHPE. Professor Ling is a professor of tribosensing and head of the National Centre for Advanced Tribology at Southampton University. She has over 20 years of research experience in tribology and condition monitoring, and has led a large number of research projects funded by the EU, UKRI, and industry. She's published over 100 research papers, is a chartered engineer and a fellow of BINDT. She's a recipient of the 2017 Commodit Prize and the 2020 Donald Julius Growen Prize from IMechE. So in terms of an agenda, we'll start with our speakers' presentations, and then we have some videos from Optimal Instruments, our partner, before the Q&A session at the end of the event. A quick note on questions: please type these into the chat, and they'll be marked for the question and answer session. We are planning to go around 60 minutes in total today. We do apologize if it does overrun. So just a quick reminder about our website, surfaceventures.org. It features videos from our previous talks, information regarding upcoming webinars, and info about the Surface Ventures team. We always like to learn a little bit about you, our audience, essentially. Hence, there'll be a quick poll appearing on your screen. As with previous events, can you please answer the question that should pop up on your screen right about now? What is your current job role? Great. We have quite a wide mix of different roles. So on that note, I'd like to hand over to our first speaker for today, Professor Ling. Over to you.
Hello. Hi. Hello, everyone. Thanks, Thomas, for the introduction. Thanks for inviting me to this webinar. And it's an honor to give a talk on the research we're doing at Southampton. The title of my talk is Integrated Intelligent Bearing Systems for Ultra-High Propulsive Efficiency Ground Demo. So this work has been done at Southampton with a team of people in both mechanical engineering and electronics and computer sciences. And also we're working with Schaeffler, the bearing manufacturer, and Safran aero-engines in this project. The project was funded by EU Clean Sky program. So in this talk, I will cover a few items. Firstly, I'll give you a very brief review of the history of rolling edge bearings, covering where the bearings come from, and smart bearing concept and intelligent bearings. I realize that my talk is not actually very tight related to surface engineering, but hopefully you are also interested in smart bearings in this talk. Then I will give you an introduction about the project, the EU project, so the strategy of the research, and how we did the test on subscale and full scale, and also how we developed the intelligence for the smart bearings. Then I'll conclude with a few notes before I acknowledge the people, the teams that helped with the work. Okay, so just to start with introducing bearings. So bearings are traced back to very, very early stage ancient time. So from 2600 BC. But the first recorded sort of illustration of bearing is coming from the drawing by Leonardo da Vinci in the 1500 years. So you can see on the screen that there's a drawing of the a study of a ball bearing. So giving the design of how the ball bearing actually look like. Not until the 1794, the first patent on the bearing, which is an invention by a Wales inventor. So this is a drawing by Philip Wong's invention on the patent he had published. A ball bearing for light and heavy wheel carriages, so showing how the bearing structures look like. So that's in the nearer to the 1800 time. Nearer to the 100 years later, you can see that there's three big inventions in the bearings, including the Friedrich Fischer, the German inventor who had developed this machine for metal ball grinding. So that was the beginning of ball bearing, so modern ball bearing. So he was also the father of the modern ball bearings. And also he was a founder for Schaeffler, the FHE bearing in Germany. In 1898, that Henry Timken actually developed this tapered roller bearings. So that's a new concept of tapered roller bearings for both axial load, support axial load. So he was the founder for Timken bearings, so one of the largest three bearing manufacturers in the world. So in 1907, so the Swiss inventor Sven Winquester, he actually developed this self-aligned bearings, and he founded SKF. So those are the three major bearing manufacturers in the world. And when in the early 1900s, that's when all these inventions happened. That led to the development of rolling element bearings for machines. So basically, the bearings become a key element, components for loads of different machines, from small to large, and they are key to the world moving. So without bearings, we cannot imagine how the world could move. So instead, in addition to the different types of bearings, as I introduced with the ball bearings or roller bearings and tapered roller bearings, thrust bearings, you also can see the size of the bearing change from 1 millimeter diameter, which is probably used in those like medical applications or brushes we use every day, and up to over 4 meter diameter bearings, like in the diggers or tunnel boring machines. And they are used in all kinds of applications. So that's why they are so important to our engineering designs. Bearings are very important, but they are not actually the most expensive or valued components in the machinery. But a small damage in the bearing can lead to very big disasters in machines. So here you can see a perfect operational helicopter turn into this remain due to very small, we didn't detect bearing failures in the gearbox of the helicopter. This was reported in 2016 in Norway, an accident in a helicopter. So these kind of things do happen in loads of situations. So that's why bearing safety is extremely important for the operation of lots of machines. So that's why the smart bearing concept started, to look at how we can actually monitor the bearing, make the bearing perform better, and the reliability can be improved. So the smart bearing concept traces back to 1908 when J. Francis introduced his slip prevention regulator for rail vehicles, which was the beginning of or led to the development of the modern anti-lock braking system for wheel bearings. So this is a very initial sort of development, but not until 20 years later, a patent came out about ABS by Karl Wassel in German. Unfortunately, it was just a patent, but no product was produced based on the patent. Until 1950s, Dunlop Macrat had actually installed ABS into aircraft engines and bearing in cars when that started to become more popular. So that was the first version of what we called smart bearing, where you have bearing, you have a sensor to monitor the speed of the bearing. Then that can be used to calculate the braking distance. So building on the concept of ABS, smart bearing design has been developed over the last 30 years by all the major bearing manufacturers. SKF had the Insight and also Schaeffler and Timken. They all have different concept or different designs of smart bearings where they can put sensors in the cage, in the ring, or in the housing of the bearings. So Perpetuum had produced a wireless unit that can be bolted onto the train axle bearing to monitor the bearing conditions for trains. And this is actually a commercial product and have been used to monitor the train health, or the train bearing health. So just to summarize the development of smart bearings, it started in the 1990s when you have a couple of sensors embedded or mounted as a unit mounted on the machine to monitor the bearing performance. And 10 years later, when the wireless communication techniques started, so people started to use more sensors embedded or mounted unit in the cage or rings, and started to transmit the data wirelessly to a different location rather than on the machine. And in the last 20 years, when the energy harvesting technology becomes more and more approachable or usable, then started using self-powered sensors, self-powered units, and more sensors or network of sensors have been mounted, embedded into bearings, and using radio frequency identification chips for the monitoring of bearings. Also, there were thin film deposition techniques used to put sensors, actually printed sensors on bearings as well. So there's a lot of development in the last 30 years for the smart bearings. So I would like to differentiate the smart bearing from the intelligent bearing from the smart bearing by adding the intelligence to the bearings with embedded sensors, become an intelligent bearing.
Professor, sorry, apologies for interrupting. There seems to be a little bit of audio crackle on your your audio. I'm not sure whether that's a connection issue or something you can try to solve. We just had a comment in the chat there about it, and I'm getting it a little bit as well.
Oh, right. Sorry, I didn't notice that.
It's okay.
I can't see anything. I'm connected to the university network. Do you want me to come out and reconnect? Or?
Yes, please. Could you quickly try that? Yeah. We'll resume in a moment for all of those watching.
Sorry about that. Okay, I'll come out and
come in. Just refresh the web page. That should solve it. Apologies for the issue, everyone. Just a slight audio glitch. We'll resume in a moment. Yes, until Professor Wang returns, just wanted to remind everyone that when we resume, if you have any questions, please do type those in the chat, and I'll mark those for the Q&A session at the end. Also, be releasing more poll questions. Thank you all for answering the ones that I've released so far. And we'll also have some handouts from Optimal Instruments when we get to the partner section of this webinar. So those will be released when the videos are playing. Okay, so. Apologies, Alan. Thanks for sticking with us. Hopefully, we'll be back in a minute or two. Okay. While we're waiting for Professor Wang to rejoin, what we'll do now is we'll play the optimal videos. So I'll trigger the first one now.
Welcome to our third edition of SRE Tribo Talks. I would like to invite you to take a look at some of the many tribological solutions we and our customers have developed on the SRE test system. For example, the SRE allows you to generate tribo contacts with complex 3-axis movements and measure them in 4 dimensions. The high practical relevance of the simulation and relevant measurement data create valuable knowledge about your product. The ability to use your own prototypes and series parts in the SRE test environment is key to achieving relevant results quickly. To this end, you benefit from an installation space of 50 × 40 × 200 mm. Your components can be tempered up to 300 centigrades. Rolling bodies are found in bearings and gearboxes, often as lubricant systems, but increasingly also dry running. With the SRE, we enable you to screen your greases and coatings under realistic load collectives with relative speeds up to 1 meter per second. Using multi-axial movements and test setups, you can transfer complex movement sequences to model testing in the SRE and thus test the real system on a laboratory scale. The results can be transferred directly into practice or simulation. A very well-known example of such movements is the piston-pin rod-eye contact, Here, the SRV allows you to simultaneously test pin materials, bearing materials, and engine oils in one test setup. Tribological model tests provide insights into tribological systems that are otherwise difficult to access. The simulation of internal engine wear processes outside the engine is an impressive example of this. The metallurgical properties of your materials under the influence of temperature can be analyzed in a range from -45 to +1000 centigrade. The simulation scope varies from simple abstracted test geometries to original parts. The test setup shown is used to evaluate high-temperature materials in plain bearings. The SRV's ability to represent tribocontacts extremely realistically in a model environment is one of the reasons for this worldwide success. Do not hesitate to call us if you want to address a friction and wear related problem through tribo testing. We will be happy to support you.
Hello, everyone. So that was the voice of Gregor Panzer of Optimal Instruments describing the capabilities of the SRV platform. Professor Wang has now rejoined us, so I'll invite her to return to the stage, and we can hopefully resume the presentation. Welcome back.
Hi, can you hear me?
Yes, we can.
Hi.
I will bring yours.
Is it too noisy?
It's absolutely fine now, so let's resume.
Okay, I'm really sorry. I have no idea.
It's okay. It's little errors like this happen. I'll leave stage and let you continue.
Okay, thank you. So I just pick up from the smart bearing that meant that the bearing has embedded sensors. So you have multiple sensors, maybe with wireless communications and energy harvesters that provide power. But to become an intelligent bearing, that we wanted the brain to be implemented into the bearing. So this is a drawing that illustrated the project that we're doing in the I2BS project. So we wanted to develop an integrated intelligent bearing where you have bearing with embedded sensors, wireless communication, power in the engine, which will be mirrored by a digital twin of the bearing that use artificial intelligence techniques to analyze the data wirelessly and then provide the prediction of the engine bearing health automatically. So that's the idea that becomes intelligence, because you have the intelligence to tell the engine what conditions the bearings are and how you can improve or change the conditions that the bearings are operating at the moment. So that's the change from the smart bearing to intelligent bearings. So in the EU project, so we were aiming to develop smart bearings which equipped not only sensors but also energy harvesters, wireless data transmission techniques, and also to develop the intelligence that can predict the health of the bearings in the aero engine. This is an image from the Safran illustrating the ultra-high propulsive efficiency demonstrator. So we're looking at the zone in here in the engine, where you have the challenges of high temperature. So the bearing, the environment that the bearings are operating at is up to 200 degrees, which would eliminate most of the electronics, because the electronics are most of them are working under 80 degrees. So that's very challenging for electronics. And also the bearing speeds are in the full scale is probably up to 3,000 RPM, but in the subscale testing for the same DM, it's actually over 10,000 RPM, so it's extremely high speed as well. And also within the engine, you would have the vibration from the engine, and also you have the vibration noise from the environment that the airplane is flying. And also within the engine bearings, so you need the oil lubrication, so you have the harm or hazardous caused by the oil as well. So the sensors have to survive in those environments. One of the things that we discovered during the project at the beginning is that adding any weight or space is limited in the airplane. Although you think the airplane is very big, but within that environment, in the chamber of the engine or the gearbox, there's no spare space at all. So finding a space or adding any weight is just not possible. So very, very challenging to make a smart bearing, intelligent bearing that not actually occupying more space or adding more weight. And also for the wireless transmission, there was a lot of metal around. So transmitting is very challenging as well. But for this talk, I'm going to focus on the sensor side and using artificial intelligence to make the sensor more intelligent. So I'm not going to talk very much on the development in the energy harvesters and the wireless transmission side of the project. So the project was operated in 3 steps. So initially we had to design the whole system, so including the bearing design, the sensor design, the power provision design, and data communication. Then we tested or implemented the design on the subscale rig, then did all sorts of tests that simulate the operation of the bearings in engines. We developed the intelligence to predict the bearing faults or detect the bearing faults based on those data. Then we commissioned the test on the full-scale rig and ran limited number of tests and validate the models that we developed from the subscale. So in terms of the test, the subscale test was conducted on the purpose designed belt-driven bearing test rig. So these were images of the test rig where the bearings are, and we also added a noise or vibration by adding a shaker that shakes the shaft. So this is a 3D model of the smart bearing, where you can see we have strain gauges mounted on the outer ring and also on the housing, and we have accelerometers mounted on the housing of the bearing connected to the outer ring here. And we have speed sensors, shaft speed and cage speed sensors that's mounted outside the bearing for the speed monitoring. The bearing we used were 3-point split ring ball bearings, and the pitch diameter is 75 millimeters. So this is a picture showing how the sensors are mounted in the just before they were putting into the test rig. You can see laser wires were still used just for insurance that we can actually get data without. So because we wanted to test the wireless in the same time as the sensor technology, so we don't want to risk with that, just test without the cables. So you can see how many cables could come into the system when you have no wireless communication technologies. So this is the image of the full-scale test rig AN62 at Schaeffler. So the test was using 2 angular contact ball bearings, and this is an image showing where the sensors have been mounted on the bearing as well. So we have, again, we have accelerometers, strain gauges, we have thermocouples, and the speed sensors. And also we added fiber optical grating, fiber bragging gratings on the outer ring of the rig bearing to test to check their ability to monitor the strain on the ring as well. Next one. So in terms of test conditions, on the subscale, we were able to test the 3 loads. So here shows the 3 loads we tested. Within each load, we actually varied the speed 3 times as well. So you can see the speed was 5,000, 10,000, and 14,000 RPMs. So the total test duration was about 6 hours each, and we ran over 18 tests, including repeats. So every condition we wanted to repeat it as well to see the signal, how repeatable the signals were. For the full scale, we ran the typical flight cycles, including the ground idle, takeoff, climb, flight idle, reverse, ground idle. So all the conditions involved in different steps were simulated in the full-scale testing. And we were going to test the bearing for maximum 150 hours, but later on you see that the test actually failed much earlier than we expected to run for. But that was probably one of the things we wanted to do anyway. We wanted the bearing to fail. We wanted the seeded defect to lead to the spore anyway, so we can see the changes of the conditions, so we can actually analyze it. So we did only 4 tests on the full-scale bearing, a full-scale rig, because the cost is really, really expensive. So here's to show you the, with the test on the subscale bearings, we have simulated damages on the inner ring, outer ring, and bore of the bearings. So you can see this is the laser ablation sort of technique generated defect on the ring, and this is after test. So within the 6-hour test, we didn't see any significant growth of the damage in the bearing. So we assume that anywhere in the signal we collected within that 6 hours, they are not changing. They have very small changes anyway. So the reason that we did that, this is an image from Schaeffler. They took this image from a real engine that the damage found on the bearing. So basically we're saying that the damage size we simulated was compatible to those that happened in services. So for the full-scale test, we actually put indents, an array of indents in the inner ring to make sure that the ball will roll over the damage, and also we generate a shoulder height on the indent, so we can it can guarantee the spore of the bearing as well. So that's what we did. With the limited number of tests we could run, that was the strategy we took for the testing. So in terms of the sensor data acquisition, we used the Dewey 43 units to collect the data, and the sampling rate was all the channels that what we monitored was at 100 kilohertz rate for 1 second duration every 30 seconds. So that's for all the tests we have conducted, both the subscale and the full-scale tests. So I wanted to go back to the intelligent bearing part. So to add the intelligence to the smart bearing. So initially you need to select one of the machine learning tools, and using that to see whether it can improve the detection of faults. So then we wanted to select appropriate inputs for the model chosen, and train the model with the features selected, and or you can choose the raw signal to train the model, and then to do the model validation and testing with new data to finalize the model for the bearing fault detection. So we did develop the model on the subscale test rig because we had loads of data, and to actually work on the full scale, because you can see they are totally different bearings and totally different sizes and totally different operating conditions. So the challenge for the using machine learning is that how you can translate or transfer your one model to another, different operating conditions, different sizes. So that was the challenge that we were facing, how we can translate our model developed in the subscale to the full scale, because the full scale test, we only have 4 tests, as I mentioned earlier. So that was the challenge we faced. Just to go back a little bit about the machine learning based model methods for bearing fault diagnosis. Obviously, in industry, people have been using different conventional signal processing techniques to diagnose the bearing fault. So they do work, but there are lots of challenges to do that. So recently people start to look at using machine learning based techniques to do this, to improve the diagnosis. So this goes back to the 1940s when artificial neural networks was introduced by McCulloch and Pitts, but that wasn't used for bearing fault diagnosis. It was just people thinking, oh, we should have some computer networks that's similar to the human brain sort of thinking network. Not until 1970s that the artificial intelligence was originally developed. And that was the first thinking about being intelligent, making computer more intelligent. Over the next 20 years, in the artificial intelligence, they were mainly using expert systems, fuzzy logic, and artificial neural networks for the in the artificial intelligence domain for the other applications. Okay, so with the bearing fault detection or diagnosis, it didn't come into public domain until 1991. So this was probably the first paper published related to using a neural network for a bearing fault diagnosis. So basically the bearing fault diagnosis using machine learning based methods only started 30 years ago. Just over 30 years ago. And over the last 30 years, that there's loads of methods have been developed and improvement have been made, mainly focusing on the feature extraction methods. So what features are the best for bearing fault diagnosis using machine learning based methods, and also what type of models should be used and what activation functions should be used. How can you speed it up? How can you transfer the learning from one system to another? So there's loads of development have been attempted, made. So the achievements to date are the high accuracy. So if you read the papers in the literature, everyone claims their methods are very effective, so they can detect the bearing faults 100% or 95%. So everyone has achieved very high accuracy. But the challenges are, so loads of developments are based on certain data. So the data are limited and the generalization ability is none of them have shown very good generalization ability, which I meant that translate from laboratory data to, for example, the applications. So artificial intelligence and the machine learning overview, I'll just give you a very quick overview for this before I talk about the methods. So artificial intelligence can be separated into two categories. One is the good old-fashioned AI and one is machine learning based AI. For the good old-fashioned AI, that mainly are the symbolic types of AI. So they are using rule-based or expert systems, this kind of method. Bayesian can be the simple Bayesian techniques is statistic, can be in the statistic-based machine learning, or is in the very early stage. It was used in the good old-fashioned AI techniques. With the machine learning techniques, we can separate them into pattern-based, so pattern recognition-based, or look at statistics-based. So the statistic-based, looking at different methods, different distributions, including the naive Bayes and decision trees or k-nearest neighbors. All these techniques, Gaussian mixed models or logistic regression. So all these are based on the probability or distribution of the data to find their relationships. The pattern recognition based are like support vector machines or neural networks or deep neural networks. All these techniques that you don't have described sort of distribution or method. It's just a black box that you just put the data in, you design a network, and the network will train and give you the results you wanted. So this is a separation of the techniques. In the deep learning, you would probably have the multi-layer perceptrons or convolution neural networks or recurrent neural networks. So all these deep learning neural networks are you have more than two hidden layers, then they are actually called deep learning. It's similar to the not shallow ones, but just to have more layers, more neurons, and more bigger networks to work on the more complex problems. So the good advantage of using the good old-fashioned sorry, not the advantage, a disadvantage of using the good old-fashioned AI is that it does require human intervention, because the rule base is that we define, if this happens, then you give that result, or symbolic, giving a different interpretation of the features. For the statistic-based, that they have the advantage of not need hyperparameter training, and could provide a physical explanation. That's the good one of the best things that statistic-based techniques they have, is can provide a physical explanation, which the pattern-based techniques don't have. But they do need a certain level of predefined conditions as well. So like the decision tree, you have to say, okay, from here, if level over this is that, level below this is the other one. So you do have to define all these parameters for it to work. So with our work, I wanted to show the result we achieved using the logistic regression methods. So it is obviously a statistic-based methods. You can use that as part of the machine learning method for the bearing fault diagnosis as well. So we're actually using the multinomial logistic regression, not the binomial logistic regression, which I'll show you the results in a minute. So in terms of developing the intelligence for the bearing fault diagnosis, we have developed a novel method to extract features from the bearing vibration signals using a combination of the substrum pre-whitening and the high-pass filtering methods to replace the original high-frequency resonant technique. As I mentioned before, the HFRT has become a industrial realized or used method that for bearing fault diagnosis is very powerful, but it has the disadvantage of you have to define the resonant frequency very correctly to be able to detect, diagnose the small features, for example, small faults, I mean. So here is just a flow chart to show how the new technique works. So basically you go through route A using the substrum pre-whitening method, and going through all the data, create a spectrum, and also you use the same data, go through the high pass filter and go through all the enveloping, and then get a spectrum here. So they add the two together, you create a joint scaled spectrum to look for the features that are related to the bearing characteristic frequencies. So I'm going to show you, so this is the machine learning part. So as I mentioned earlier, we're using the logistic regression, multinomial logistic regression model for the prediction of the faults. I will not go through all the mathematical details. Basically, we're using a series of functions to calculate the coefficient for different features, then work out which feature is the best and how we can classify different faults into different classes based on their the contributions from each features. So I'm going to give you some examples of results that we extracted the bearing characteristic frequencies using the new method. Firstly, from the subscale tests. So this is showing a waveform from 1 second data. So you can see it's 100,000 data points, because the sampling rate was 100 kilohertz. The test condition was shaft speed was 5,000 RPM and the actual load was 9 kilonewtons. So this is the waveform. You can't really see very much from here. This test was from a test with a ball damage of 400 micrometer diameter. So we analyzed this one waveform using different methods, including the full band enveloping and using basic substrum pre-whitening envelope, and use high pass filter envelope, and also using improved substrum pre-whitening method. So all these have been introduced in a paper that we're going to publish. So if you're interested, I welcome you to read that and find how exactly we did these. But for here, I'm just comparing. This is the new method, the combination of the two methods with the Safran and the Safran pre-whitening and the high pass filter. So you can see here clearly that we can detect those peaks, which is related to the ball spin frequency and their sidebands. Yeah, so this is the sidebands of the BSF as well. So the new method had improved the features that we're looking for that related to the fault in the bearing. And here is a few more examples with different faults and different conditions. So you can see A is the 400 micrometer ball damage at 5,000 RPM, 9 kilonewtons, which I showed you earlier. And B is the on the outer ring and with the same speed but different load. And C is the damage, smaller damage on the inner ring and at the same speed but same load as the second one. The reason I show you same speed is because with the same speed you would have same defect frequencies, so it's easier to compare. So in this three plots spectra, you can see that this is the first one I showed you earlier, detecting the BSF and the sidebands and their harmonics. And the second one, which is have the outer ring damage, and we can detect the outer ring frequency, the BPFO and harmonics, and also the BPFI from the shaker. So the BPFI is here, so which is the sorry, wrongly. So this one is the 700. No, so this one is 740. No, sorry. So this is the 700 because it didn't start from 0. I was just confused. Sorry. So this is the BPFO, which is 740. This is a double of that. So it's the second harmonic. This is the third harmonic. You can see all the BPFO and harmonics. But the green one here is showing the BPFI 927 and their harmonics. One thing that I wanted to point out, we know they are from the shaker, not from the bearing, is because we didn't see the harmonics of this one. So that's why we said that's from the shaker, not from the bearing. With this one, you can see that it's the signal from the bearing with the inner ring damage, where you can see clearly the inner ring fault frequency and their harmonics and their sidebands very clearly here. Okay, and also we see the outer ring damage with the from the shaker as well detected. So just to show that with the new method we have extracted a better quality of features, and you will see that later on with the machine learning we are able to build a much better model as well. Just to show you quickly that we have done the full-scale tests and we analyzed the data using the new method. You can see this color map shows that, as I said earlier, with the full-scale test, we tested everything on the damage on the inner ring. So we are looking for the order for the inner ring, which is 13.5. So you can see here is the inner ring first harmonic of the inner ring damage. You can see it didn't start from beginning, but it grew from later. The test only ran for 24 hours, but the bearing was found to have spoiled. So you can see this clearly indicates the inner ring damage here. And also you can see the growth of the second harmonic and the third harmonic as well. But you would notice that we see some features at the beginning here. So this one, that one, that one, that one, the other harmonics of this frequency, which is not related to any of the defect frequencies that we were looking for. At the moment, we are waiting for the confirmation from Schaeffler to see whether it is one of the support bearing failed in the rig, but we're still waiting for that. So this has come to the machine learning part with using the multinomial logistic regression. We have trained a model using 387 data from the outer ring damage test and 361 from the inner ring damage and 189 from the ball damage. And you can see that the training results that we could achieve 100% of accuracy from the training for the model. So with this model achieved 100% of accuracy, we then tested the model with two more data with the in the literature. One is from the Case Western Reserve University. So this database has been widely used for bearing diagnosis research. And I will show you how this model works with these data. And also this is another set of data that the PhD student Amir Masood had found that we tested as well. We haven't run the test for the full-scale data yet, but we are going to do that later. So I won't be able to show you the model validation with that one, but I can show you with those two data sets. Okay, so here shows the confusion matrix for the data with Case Western Reserve University. So as you can see, the first one on the left is when we use all the data from the CWRU, we found we achieve 82.8% of accuracy. So 82.8% of the data was detected correctly. And you can see 23 of the ball faults were classified into either outer ring or inner ring faults. So this is the results we achieved with all the data. So what we found was that this is much better than the equivalent study by Randall. They showed that only 61.1% of the faults could be detected. No, sorry, 61 was this one, was detected. Much lower data could be detected. So this is, although it's not very high, but still much better than the literature reported values. They didn't use machine learning, but it was the data that they physically checked was diagnosable or not. So if you look at the middle graph here, which we run the model or using the data which is diagnosable and partially diagnosable. This is what I mentioned, that 61% was classified as in this category, but we actually were able to detect all of the data correctly into the right classes. With the other data from MFPT, you can see that 100% of the faults were classified accurately. So I forgot to say that when we did this, we didn't need to train the model again. So only put the data from the literature database to the model and see how many the cases were able to be classified accurately. So there's no new model training. So that's really exciting to see the transferability of the model. So I think I've probably overrun a lot. So I just want to conclude with a few points that hopefully you can take away from this talk. So obviously bearing is vital to many rotating machines, and their health is key to the normal operation of those machines, especially for those very high value and safety critical ones. So since the concept of the smart bearings, which is 100 years ago, then the system has evolved from just using single or multiple sensors to actually using energy harvesters and wireless communications and making them more approachable and embedded into the bearing rather than separate units onto the machine. To add to the intelligence, we can use a lot of machine learning techniques. So lots of people have been looking at it, but one thing that's challenging in the development is sufficient data. So lots of studies reported in the literature use the data that I showed in the Case Western Reserve University, but that data is not perfect. There's loads of issues with that data. So that has shown in the development. Everyone shows 100% of detection, but they're using the same data for training and same data for detection. Okay, so that's a bit of flawed. So in this project, we have created a lot of structured test data, which are tested at systematically, and that can have been used to build the machine learning model, which has been demonstrated the capability of being transferred using other designs of bearings as well. So we're yet to demonstrate or validate with our full-scale data, but we're quite confident it will be very useful. So the new method that combined the CPW and the high-frequency filtering methods have shown to be able to extract very effectively the bearing characteristic frequencies, and which has been used for the machine learning training and detection. So we are very much looking forward to finalize this generalized fault detection model for a wider range of applications without the requirement of further training. I think I just wanted to conclude my talk with thanking to the funders, which is the EU Clean Sky program, and also the Top Gear manager, Safran Aero-engines, for their support, and Schaeffler being a very fantastic collaborator and technical support. Lastly, but not least, that my colleagues at Southampton from the two different groups and the PhD student, they have made this work really, we achieved what we wanted. And thank you for listening. And I'll be ready to answer any questions you may have. Thank you.
Thank you so much, Professor Wang. So we'll move directly onto the questions, and we have a few questions lined up. Hopefully they should appear on the screen. So we'll begin with the first one is, what materials were the bearings made of?
M50.
Okay,
it's the M50, yeah, bearing steels, yeah.
Great. We'll move on to the next one. One of the most critical determining factors for bearing life / performance is hydrodynamic lubricant film thickness. Did you attempt to measure this?
Well, it is obviously one of the desirable parameters we wanted to know. But with this study, we're more interested in the later stage, not the film thickness, how the film thickness will change. So we didn't incorporate the film thickness measurement in this project, but in the future, I think it is a very valid point to look into what sensors can be used to measure the film thickness in situ to complete the smart bearing design. Yes, definitely. If you have any good techniques, you could let us know. That would be great.
Brilliant. And the next question is, what is the hardness of the bearing surfaces, and does this change after service and application? Great question.
This is a good question. We know the rough, the general hardness for M50 in the bearing is probably between 750 to 800 Vickers hardness, but we actually haven't measured the hardness after the test, after the service. So it could change, depends on what stage they are. There is a surface hardening and cold hardening, and all that process could be softer as well. So we actually don't know the hardness after service in the aero engine.
Sure.
Oh, someone has put in 56 to 65, which I think is probably 600. It should be 100, not. Maybe you're using the unit is. It shouldn't be HPE. You're using rock hardness, was it? I think 56 to 65 should be the Rockwell hardness, not the Vickers hardness. Yes.
I think the person has clarified.
Yeah.
It's Harness and Rockwell. Great. Our next question is, final two questions. Change in resonance occurs once a fault, bracket spall, has already started to develop. What work has been done to look at sensing methods to avoid damage occurring in the first place?
Yeah, that's a very good question. So this project has been focusing on detecting the faults. We have also other projects looking at how we can avoid, how we can improve the performance of the bearings, of course. So we have project looking at using different materials to perhaps to avoid the damage. I think, okay, I just look at your question is actually once it started, how to avoid. So depends on what mechanism the failure is. For example, we detect the spall or we detect the damage due to dry lubrication. We can add more lubricant to the system to correct the lubrication. If it's due to load, we can adjust the load, or due to other parameters. So the whole point of the smart or intelligent bearing is that you detect the fault and know the reason for that. Then we can correct it and change the performance, change the operation of the system, then make the system work for longer, life.
Brilliant. And our
Hopefully
final question. Sorry. Our final question is, how can you prevent the onset of RCF pit damage?
That's so the onset of damage obviously normally is because the operating conditions are not at their optimal conditions. So you either have hard particles goes into the contact due to other contamination, or due to initial other parts of damage went into that. You could have, as I said earlier, the lubrication wasn't sufficient. So this happens. It doesn't happen in the real situation. So the lubricant supply wasn't enough, or the temperature was too high, and the film thickness becomes very thin. So they can all lead to the onset of pits on the surface. There are also, obviously, you have the subsurface lead initiated failures as well. That's more due to other situations. So we have done lots of study looking at the subsurface initiated RCF as well. So there's loads of conditions that could lead to that. Yes. So to prevent it, you would have to make sure you monitor the operating condition and make sure they are operated at the desired conditions, rather than something happened that you didn't know and it continues. That's often what happens. So if you don't know what had gone wrong and continuously running at that condition, would lead to the damage of the systems or bearings.
Brilliant. Thank you for all the questions, everyone. We appreciate them. I'd like to thank once again Professor Wang for your engaging talk. We really appreciate your time and for sharing. We'd also like to thank Optimal Instruments for supporting this webinar. They're our partner. Please do remember to visit our website, where previous talks and this talk will be available to watch again. We'll organise the next webinar on the 30th of June, so please stay tuned on our website, emails and LinkedIn for further updates. We also have a fortnightly newsletter, Modern Surface. By signing up to our mailing list, you will receive this. We also ask for your support to take the time to advertise these lectures to your contacts. So on that note, thank you for joining us, and we hope to see you again next time. But for now, enjoy the rest of your day, and hopefully we shall see you soon. Thank you, everyone. Bye.
Bye.